Good morning, Muhammad Hawa is here. Let's discuss today the magnitude and phase spectrum for Fourier series. Remember that we looked at several examples of periodic signals x of t and we found the complex exponential Fourier series coefficients. This was one of those examples. X of t is equal repeated rect, which looks like this. We managed to find the complex exponential Fourier series coefficients, and they turned out to be a tau over t naught sinc and omega naught tau over 2 pi. And if you substitute the specific a, tau and t naught for this example, here we have a equal 2, tau equal 2, and t naught equal 4. What you're going to get is alpha n equals sinc n over 2, which is a general equation for alpha n that allows us to calculate alpha naught, alpha 1, alpha 2, alpha 3, and so on by substituting the proper value of n. If you substitute n equals 0, you're going to get alpha 0, which in this case turns out to be 1. Or if you substitute n equal 1, you're going to get alpha 1, which is 2 over pi. Or alpha 2, which is 0 here, or alpha 3, which is minus 2 over 3 pi, and so on and so forth. Of course, alphas are complex numbers in general, so you can isolate them into magnitude of alpha and phase shift of alpha. We did all of that for several examples earlier. That's good and very helpful. However, usually a picture is worth 1,000 words. That's why it's a good idea to visualize the harmonics represented by those alphas. And to visualize the harmonics that are scaled by the coefficients alpha n, we typically plot the magnitude of alpha n of such complex number for the nth harmonic versus the frequency of such harmonic, meaning n omega naught. This is very much like trying to plot the absolute value of alpha n versus n, but rather than using n, we're going to use the frequency n omega naught. So we have a diagram showing us the magnitude of this complex number, this coefficient, versus the frequency of the harmonic scaled by this alpha n. And we call this diagram the magnitude spectrum of the signal x of t, or sometimes the double-sided magnitude spectrum or two-sided magnitude spectrum because it has two sides. Some textbooks refer to it as the amplitude spectrum or the double-sided amplitude spectrum or the two-sided amplitude spectrum. Some textbooks even call it the line spectrum, but they all mean the same thing. It's the absolute value of alpha n sketched versus n omega naught, the frequency of the harmonic. Here is my double-sided magnitude spectrum or the alpha n's for my repeated rect example that I've shown you. Here I draw the value of alpha naught versus frequency 0, and alpha 1 versus frequency omega naught, alpha 2 for frequency 2 omega naught, alpha 3 for 3 omega naught, alpha 4 for 4 omega naught, alpha 5, 5 omega naught, and so on. I also remember to draw alpha minus 1 for minus omega naught, alpha minus 2 for minus 2 omega naught, alpha minus 3 for minus 3 omega naught, alpha minus 4 for minus 4 omega naught, and so on. That's why it's called double-sided. It includes the positive frequencies where you get alpha 1, alpha 2, alpha 3, and so on, and the negative frequencies for n negative, alpha minus 1, alpha minus 2, alpha minus 3, and so on. Notice that I draw the absolute value of the alphas. For example, the absolute value of alpha naught was 1, while the magnitude of alpha 1 was 2 over pi. The magnitude of alpha 2 was 0. Alpha 3, the magnitude is 2 over 3 pi. Alpha 4 is 0, and so on and so on. This diagram of the absolute value of alpha n versus the frequency of the harmonic is what we call the double-sided magnitude spectrum. And you might have noticed an interesting relationship between the positive side of the spectrum and the negative side of the spectrum if x of t is a real valued signal, like in my example. Because if that is the case, then alpha minus n, the negative part, is equal alpha n conjugate, which means the magnitude of alpha minus n is the same as the magnitude of alpha n. In the conjugate, the phase is the negative of the phase, but the magnitudes are the same. Hence, the magnitude spectrum will turn out to have even symmetry for x of t real valued signals, which are the ones we use in real life. Please remember this about the double-sided magnitude spectrum. In this diagram, I put the numerical values of the absolute value of alpha n next to the corresponding line. For example, for alpha naught, I put 1 here. For alpha 1, next to this line, I put 2 over pi. Next to this line is 0. And next to this one, I have 2 over 3 pi, and so on. But sometimes it's helpful to think about where those values came from. And hopefully you remember that those values came from the sinc function, because the sinc was the answer for my general alpha n. That's why a lot of times you'll see the magnitude spectrum drawn with an envelope. It's this dotted line here, which shows you how the alphas change. In my case, the alphas are controlled by a sinc, and that's why you see the envelope here, or the dotted line, being absolute value of a sinc. Remember please that the envelope is not part of the alpha n or the magnitude spectrum, but it helps us visualize the behavior of those alpha n's. And visualizing this behavior can be quite helpful. For example, later on I'll show you it helps you calculate the bandwidth W of the signal x of t. So if you see a magnitude spectrum with this dotted line, please remember this is just to help you understand how the different alpha n's behave. It's not actually part of the spectrum. The spectrum is those lines with certain magnitudes dependent on the values of the alphas. Another important fact to understand about the magnitude spectrum is that those lines are drawn at multiples of the fundamental frequency, because the harmonics exist at multiples of the fundamental frequency. So the separation between this line and this line is omega naught. And the separation between this line at omega naught and this one at 2 omega naught is also omega naught. And between this one at 2 omega naught and this one at 3 omega naught, the spacing is omega naught. So the separation or the spacing between the lines in the magnitude spectrum is actually the fundamental frequency of the periodic signal, which is omega naught equal to pi over t naught. Please be careful when drawing the magnitude spectrum and space the lines equally using omega naught. In addition to drawing the magnitude of alpha n, we typically plot the phase of this complex number alpha n versus the harmonic frequency n omega naught. This diagram of the phase is called the phase spectrum of x of t, or the double-sided phase spectrum, or the two-sided phase spectrum. Please remember that if x of t is real valued signal, then you're gonna get alpha minus n equal alpha n conjugate, which means that the phase shift of alpha minus n is equal minus the phase of the complex number alpha n. Hence the phase spectrum has odd symmetry, not even symmetry like the magnitude spectrum, but the phase spectrum has odd symmetry. Be careful when drawing the phase spectrum. You need odd symmetry for real valued signals, while for the magnitude spectrum you need even symmetry. I show you here the double-sided phase spectrum for my earlier repeated direct example. Notice that the phase of alpha naught is 0, the phase of alpha 1 is 0, the phase of alpha 2 is 0. The phase of alpha 3 on the other hand is pi, or 180 degrees. Because I have odd symmetry, the phase of alpha minus 3 is actually the negative of alpha 3, which means it's minus pi. Same thing happens for the 7th harmonic, where the angle of alpha 7 is pi, but the angle of alpha minus 7 is minus pi. Since I'm drawing the angle or the phase versus the frequency of the nth harmonic, the separation or the spacing between the lines is again the fundamental frequency omega naught of the periodic signal x of t. Please remember that the magnitude spectrum and the phase spectrum of a certain signal x of t are what we call the frequency spectra of x of t, which are the frequency domain representation of x of t, because they tell you about the behavior of the harmonics included, whether you're describing the magnitude of those harmonics or the phase of such harmonics. In certain simple examples, alpha n turn out to be a simple complex number. I'll give you an example. What if alpha n is a real value? A real number is a special case of a complex number that has a certain magnitude but a phase shift of only 0 or pi. The phase shift is 0 if the real value is positive, while the phase shift is pi if the real value is negative. So it's really not necessary to draw the magnitude spectrum and the phase spectrum. We can combine those into one diagram. I'll call this diagram the amplitude spectrum to distinguish it from the magnitude and the phase spectrum. Here is the double-sided amplitude spectrum for my repeated direct signal. Because my repeated signal gave me alpha n's equal sinc, and the sinc is a real value, I just sketched the sinc as positive values and negative values instead of splitting this real number into magnitude and phase. Sometimes one diagram is enough for those simple cases and you don't have to draw both the magnitude and the phase spectrum. The amplitude spectrum is quite enough. However, if you end up with alpha n's being complex number that is more involved, then it might be a good idea to split this complex number into the magnitude spectrum and the phase spectrum and see each diagram individually. And it's important to remember that when you look at a magnitude spectrum or amplitude spectrum, what you're looking at are the harmonics representing the signal x of t. Remember that x of t consists of a DC value plus infinity cosines. This line, the line at zero frequency, which is alpha naught, is actually the DC value of x of t, or the average value of x of t. So when you look at this line, please remember that you're looking at the DC value of the signal. On the other hand, if you look at this line and this line combined together, you're looking at the first harmonic, the first cosine included inside x of t. Also, if you look at this line and this line, you're looking at the third harmonic, the cosine with the frequency 3 omega naught included in x of t. So every pair of lines at frequency omega equal n omega naught and minus n omega naught represent one cosine signal. That's the nth harmonic. And that's why we have infinity lines, because we have infinity cosines. Every pair of lines, one at positive frequency, one at negative frequency, are combined together to create the nth harmonic or the cosine at frequency n omega naught. So why do we say we need a pair of lines to represent a cosine? And why do we have positive frequency and negative frequency? Actually, there is no such thing as negative frequency. Rather, we need to combine alpha minus n with alpha n to create a single cosine at positive frequency. I hope you remember that alpha n and alpha minus n are the coefficients that we multiply by e to j n omega naught t and e to minus j n omega naught t. If you add this line and this line, what you're gonna get is a cosine. Let me show you. Alpha n is a complex number with a certain magnitude and phase. Alpha minus n is also a complex number with a magnitude and phase. But please remember, if x of t is real, then alpha minus n is equal alpha n conjugate, which means the magnitude of alpha minus n is the same as the magnitude of alpha n, while the phase of alpha minus n is equal negative of the phase of alpha n. Now let's combine this exponential with this exponential, as you can see here, and let's combine this exponential with this exponential. The exponents add up like you see here. And let me take the absolute value of alpha n outside as a common factor, multiply by 2, divide by 2. This e to j plus e to minus j is simply a cosine from Euler's identity. So you're going to get cosine n omega naught t, where n omega naught is the frequency of the nth harmonic, plus the angle of alpha n, which is minus theta n in the compact form. The 2 alpha n is the magnitude of the compact form Cn. So the absolute value of alpha n is giving you an indication about the magnitude of the cosine, while the angle of alpha n is giving you an indication of the phase shift of the cosine. But we need the negative side because we need to combine e to j plus e to minus j to get an actual cosine. If you only have positive side, you get complex number and you never get the cosine. So we need a pair of lines in the double-sided magnitude spectrum to be able to get a cosine representing the nth harmonic. So in summary, the magnitude and phase spectra are saying that the periodic signal x of t can be expressed as a sum of sinusoids or harmonics of the frequencies omega naught, 2 omega naught, 3 omega naught, n omega naught, and so on. Plus, of course, zero frequency, which is the DC component. Those harmonics have varying amplitudes and phase shifts for the different harmonics, which we show in the magnitude spectrum and the phase spectrum. By the way, if you do not like to draw a pair of lines to represent one harmonic, you could plot the amplitudes from the compact Fourier series coefficient Cn versus the nth harmonic frequency n omega naught. What you're gonna get is what we call single-sided magnitude spectrum or one-sided magnitude spectrum, or sometimes single-sided amplitude spectrum or one-sided amplitude spectrum. If you want to get one-sided phase spectrum, then please plot the phase shift of the compact Fourier series coefficients theta n for the nth harmonic versus the frequency of such harmonic n omega naught. This is of course the single-sided phase spectrum or the one-sided phase spectrum. Here I show you the difference between the double-sided magnitude spectrum and the single-sided magnitude spectrum. Notice in the double-sided magnitude spectrum, I draw the absolute value of alpha 0, absolute value of alpha 1, absolute value of alpha 2, absolute value of alpha 3, and so on. Also the absolute value of alpha minus 1, alpha minus 2, alpha minus 3, up to minus infinity. On the other hand, for single-sided spectrum, I draw the C1, C2, C3, C4, C5, the compact Fourier series coefficients. And I don't have negative side. It's only one-sided. Because the compact Fourier series have cosines from n equal 1 to infinity. Unlike the complex exponential Fourier series, where I have n going from minus infinity to infinity. However, you'll notice that the single-sided magnitude spectrum describes similar information to the double-sided magnitude spectrum, because C1 in the compact Fourier series form is actually equal to by the absolute value of alpha 1. C2 is equal to multiplied by the absolute value of alpha 2. C3 is equal to multiplied by the absolute value of alpha 3, and so on. So the behavior of the single-sided spectrum is very similar to the behavior of the double-sided spectrum. The only slightly different behavior is for the DC component, because the DC component here is not C naught, it's actually C naught over 2, which is equal alpha naught, not 2 alpha naught. Otherwise, the information contained in the double-sided spectrum is very similar to the information contained in the single-sided spectrum. Here is also an illustration of the difference between the double-sided phase spectrum and the single-sided phase spectrum. You notice here I have values for n positive and n negative, but here only values for n positive. However, theta n from the compact form is equal negative of the angle alpha n. So instead of by here, you will have minus by here, and that's about it. The information contained in the double-sided phase spectrum is similar to the single-sided phase spectrum. Which one should you draw? I myself prefer the double-sided spectrum because it looks very similar to Fourier transform, which hopefully I'm going to show you later on. However, some textbooks prefer the single-sided spectrum. Not much difference in terms of information because one relies on the complex exponential Fourier series coefficients alpha n, but the other one relies on the compact Fourier series coefficients Cn and theta n, and both are equivalent forms to describe Fourier series. Somebody might say, how about the trigonometric Fourier series? Should we draw ANs and BNs versus n omega naught? You could do that, of course, if you want to, but not many people do that because it's more intuitive to think about a harmonic amplitude and phase shift rather than thinking about its quadrature components of cosine and sine. So I'm not going to draw diagrams for AN and BN. Whether we draw the double-sided spectrum or the single-sided spectrum, we say the frequency spectra of x of t show the frequency content of the signal x of t. They represent an alternative but equivalent way of describing the periodic signal x of t instead of as a function of time t. Rather, we are describing in the spectra the harmonic content of x of t or its constituent frequencies. The frequency spectra of a signal are called the frequency domain representation of x of t in contrast to the time domain representation, where x of t was specified as a function of time t. These magnitude and phase spectra represent a unique description of the specific periodic signal x of t Hence, if somebody gives us the magnitude and phase spectra, we can reconstruct the signal x of t using the Fourier series formula, of course. And a lot of times, just glancing at the frequency content can be very helpful. That's why it's important that you practice drawing the magnitude and the phase spectrum for Fourier series. So it's important that you understand that time domain representation and frequency domain representation are different ways of looking at the signal. So in time domain, I might say my signal is a repeated rect because I describe how it behaves in time domain. Or I could say those are the different harmonics representing my repeated rect. So I'm describing the amplitudes of the different frequencies and the phase shifts of the different frequencies, and that's called the frequency domain representation of the signal. But at the end of the day, it's the same signal. It's very much like looking at the same object from different angles, from different perspectives. And you can gain a lot of insight by looking at that object from the side view, from the front view, from the top view, and so on. And that's why we'd like always to be able to look at the signal in time domain and the frequency domain. Let me show you one advantage of looking at the signal in the frequency domain. We have many advantages, but we are going to look here at only one, which is calculating the bandwidth of the signal x of t. Bandwidth of the signal is a very important property of the signal x of t, and we'd like to know it. It's very easy to find the bandwidth of the signal x of t if you look at the magnitude spectrum of x of t, because the bandwidth is the range or band of frequencies that must be positive, of course, that contain the significant harmonics within the signal x of t. And the significant harmonics, non-negligible harmonics, are those with large enough amplitude or magnitude or large enough average power. We're going to indicate the bandwidth of x of t using the symbol b of x when we measure the bandwidth in hertz, or I'm going to use w of x when I measure the bandwidth in radian per second. Of course, remember the relationship between radian per second and hertz is multiplying by 2 pi. Let me show you how do we calculate the bandwidth b of x or w of x from the magnitude spectrum of a signal. But before I do that, a few warnings. Be careful about the difference between calculating bandpass bandwidth versus baseband bandwidth. What I'm going to explain in this video is baseband bandwidth. Later on, hopefully, in a more advanced course, you'll see the difference between calculating bandwidth for bandpass versus baseband. Another thing to keep in mind is that bandwidth is quite a generic word. Sometimes we use it to describe the bandwidth of a device, like the bandwidth of a filter. But that's different than what I'm going to teach you here, which is the bandwidth of a signal. The bandwidth of the signal is easily calculated by looking at the magnitude spectrum or the amplitude spectrum of the signal. Being able to calculate the bandwidth of the signal is quite important. It helps us in a lot of scenarios, like sampling, filtering, in a transmission over communication channels, and so on and so forth. So let's try to calculate bandwidth. This example says, for the following frequency domain representation of x of t, where I'm given certain alpha n's, 5 rect n omega naught over 6 pi. If you try to draw it, you'll get this magnitude spectrum, absolute value of alpha n. Please determine the fundamental frequency of the signal and its bandwidth. This is quite a simple example. Notice in this spectrum that I have a certain DC value represented by the line at 0 frequency. I have another cosine here, this pair of lines, and a third cosine here, which is this pair of lines. So I have a DC and 3 significant harmonics. But the fourth harmonic has an amplitude of 0, and the fifth harmonic has an amplitude of 0, sixth harmonic amplitude of 0, and seventh harmonic amplitude of 0. Those are not significant, of course, harmonics. So this band of frequencies is what we call the bandwidth of the signal. This positive range of frequencies, which includes all the important harmonics, is what we call the bandwidth. So as a rule of thumb, if you see non-zero harmonics followed by all zero harmonics, this is the point where your bandwidth is, which in my case is a 3 omega naught. So the bandwidth Wx in radian per second is a 3 omega naught, where omega naught is the fundamental frequency. So it is the spacing between the lines. From the equation here, I can tell that the width of this whole rect is 6 pi. So this Wx, the positive range of frequencies, my bandwidth is actually half that much, which is 3 pi radian per second. If you want omega naught, the fundamental frequency of the signal, then you say 3 omega naught is 3 pi. This tells you that omega naught itself, which is the spacing between the lines, is equal by radian per second. In this second example, I changed things a little bit. Notice here that alpha 3, the third harmonic, is 0 this time. Please determine the bandwidth of the signal and its fundamental frequency. A lot of students think because there is a 0 here, this is the bandwidth of the signal, which is wrong. Because we still have a fourth harmonic that is significant. This harmonic is important. You want to count it as part of your bandwidth. So the bandwidth Wx is equal 4 omega naught in radian per second. After 4 omega naught, all the harmonics are 0. They are not significant. If I say what is the fundamental frequency of this periodic signal, you say it's the spacing between the lines. And in this case, the spacing is 2 radian per second. So omega naught is 2 radian per second. And the bandwidth is 4 omega naught or 8 radian per second. In this third example, the magnitude spectrum is a triangular shape, where alpha n's are 7 delta n omega naught over 5. Some students look at this 5 and they think this is the bandwidth. But if you look at the actual diagram of the triangle, 5 and later we have 0 harmonics. So they are not significant and the bandwidth is up to this point, which is 4 radian per second. The fundamental frequency where my first harmonic is 1 radian per second. It is also the spacing between the successive harmonics. Now this one is a very interesting example because I give you a sink envelope controlling the alpha n's. Where is the bandwidth? We know that the sink reaches 0 only at infinity. So we don't have a point where all the harmonics become 0 all the way to infinity. However, if you ever sketched a sink, you notice that those values are extremely small. And that's why a lot of people consider them very close to 0. They say those are negligible. Anything beyond the first null is considered almost 0. And that's why the bandwidth in this example is 20 radian per second. That's the correct answer for the bandwidth. I know it's an approximation. Those harmonics are not exactly 0. But this approximation is what many people use. When they see sink as an envelope, or sink square, or sink to the power 3, they say the first null is your bandwidth. Anything beyond that bandwidth is considered so small, almost 0. By the way, this is slightly different than our earlier example. We don't stop the bandwidth at 15 radian per second, and we say this is 0 negligible. For the sink square, sink to the power 3, consider the first null as part of the important components because this is what people do. It's still an approximation. I know it's not a perfect answer, but you will see later on when we talk about Fourier transform, this approximation makes quite a lot of sense. If I say what is the fundamental frequency, which is different than the bandwidth, the fundamental frequency is the spacing between the lines. And it's also the frequency of the first harmonic. It is 5 radian per second. Alright, let me give you some homework to practice. Consider x of t, repeat every 5, 3 delta of t over 2.5. This equation is the time domain representation of x of t, which gives you this diagram. This signal is a signal that we solved earlier, and we managed to calculate the alpha n's, which turned out to be alpha n equal a tau over t naught, sink square n omega naught tau over 2 pi. And if you substitute a tau and t naught, you're going to get 3 over 2 sink square n over 2. What I want from you guys is to calculate the different alphas from this equation. So find alpha naught, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and so on. And then from those complex numbers, find the magnitude and the phase. And once you calculate the magnitude and the phase, draw the magnitude spectrum and draw the phase spectrum. From that, find the bandwidth and find the fundamental frequency for this specific example. By the way, if it's only the bandwidth, that you're after, there is a simple trick to be able to calculate the bandwidth without drawing the magnitude spectrum and the phase spectrum, because we know that for a sinc or sinc square, the bandwidth is at the first null. And we know that the first null occurs when you put 1 here inside the sinc square. So when this argument of the sinc square is equal unity, you're gonna get your first null. And that happens when n omega naught is equal to pi over tau. Because if you put 2 pi over tau here, 2 pi cancels out with the 2 pi, tau cancels out with the tau, you end up with sinc square 1, that's your first null. That's why the bandwidth will turn out to be at 2 pi over tau. And I know for this example tau is 2.5. As you can see here, if I ask you to calculate bandwidth in hertz, all you have to do is divide this number by 2 pi, so the bandwidth is at a value of 1 over tau in hertz. That's why people like to use the first null as a good approximation for the bandwidth. Finding it is so simple. So long as you set the argument of the sinc square equal unity, you'll be able to quickly determine what is the bandwidth of the signal. One last homework. This signal x of t is a repeated exponential. As you can see here, this is the time domain representation. Please draw this time the single-sided magnitude spectrum and the single-sided phase spectrum. What do you have to find to be able to draw the single-sided spectra? You need to find the compact form of Fourier series. You need to find the CNs and the theta n's. Once you manage to find the CNs, here is the right answer, and the theta n's, here is the right answer, which by the way can be easily obtained from the alpha n's. Once you have the CNs and the theta n's, draw the single-sided magnitude spectrum and the single-sided phase spectrum. You'll see you only have positive frequencies and not negative frequencies. Here are the correct answers. Please try it first and then compare your answer to this one. Thank you very much for listening. If you have any questions, leave them in the comment section. Goodbye.